Welcome to Hot Chips 2024. Session 1. High Performance Processors Part 1.
All right, hi everyone. I'm happy to kick off the first session of Hot Chips 2024. This is the High Performance Processor session. My name's Ian Brott. I'm here in my capacity as a role as a Hot Chips member and not under that of my employer. So my first speaker I'd like to introduce is Gerard Williams III. Many of you know Gerard. He's the SVP at Qualcomm, where he is the lead for the Oryon CPU, which is part of the Snapdragon X Elite platform. Gerard's career started with Intel and TI, where he then moved on to ARM, where he became an ARM fellow and influenced many ARM products and served as a technical advisor for many ARM partners. He then moved on to Apple, where he was senior director and chief CPU architect for nearly 10 years, steering the development of many CPUs and SoCs and setting industry benchmarks. And before his role at Qualcomm, Gerard co-founded and led Nuvia, which was a startup that redefined server CPU technology. He holds an MS from the University of Missouri-Rolla and a BS from Arkansas State University. He has 38 granted patents with many more pending. So let's welcome the speaker.
Hello, everyone. It's nice to actually be here today and get a chance to actually talk about the Qualcomm Oryon CPU and give you a feel for what we built inside this machine. With that, let me jump into the talk. So what did we actually do at Qualcomm in order to build this CPU? So it's actually a full custom CPU. It was built on 4-nanometer process. And it's a brand new design used in compute workloads and many other industries, which I'll talk a little bit about at the very end. So within the SoC, which you can see over here on the right-hand side, you can see basically the CPU complex, GPU, traditional stuff that you normally find in SoCs. But the important thing here that I want to highlight is a lot of questions that the industry has been asking. What does the CPU complex itself actually look like at a high level? It's comprised of 3 CPU clusters. They are actually the same, unbeknownst to some in the audience. One is operated in an efficient manner and the other 2 are fully performant, but the underpinnings of the design is the same. The complexes are comprised of 4 CPU cores. It has an integrated level 2 cache and an interface that talks to the system. Inside of these CPU cores that you'll see is a very classical CPU complex. The efficiency of this starts actually at a high level within the core itself. But the units themselves that make up the core, you can see in the diagram in the center, classical CPU architecture, instruction fetch all the way to memory management and load store. And the basic premise of this design, I'm going to dive into details for you here in a few minutes. The microarchitecture. So, what does each unit comprise of? What we're going to find is that it's again, classical design. You see an instruction cache in this unit, and there's a pictorial coming up, so you'll see how it's organized as well. But there's a fully coherent instruction cache, 192 kilobytes, has an integrated L1 TLB, a 256 entry structure. Many different predictor structures are built into this engine as well. Prefetching concepts are built into this structure as well. Some data structure sizes that you're going to see here. One important one that we notice is branch mispredict latency of the CPU. It's not what I call industry best, but it's balanced with the underpinnings of the design. It is 13 cycles and a return stack predictor as well. It's around 50 entries. I'm going to jump to the picture so I don't talk to a bunch of text, but this is the pictorial representation of what we've actually designed. You can see in the upper half of the diagram, that is basically the instruction cache, the predictors, the TLB structures in this design. The predictors themselves, we didn't talk about it in the slides, but I'll give you a verbal feel. It's built around Tej architecture that a lot of you have probably seen in industry papers. They feed the front end of the machine. There is a branch target buffer there as well to help redirect the machine and to get the next fetch group that the processor is going to need to feed all the downstream decoders that we see at the bottom. The machine itself basically has 8 fundamental decoders in it, and they are preparing instructions for the execution units, the load store units, and the vector unit down below. The instructions themselves, after they're decoded and executed, go through and enter into a reorder buffer that you can see along the right-hand side of this diagram. It's around 600 entries. It's a little larger than that, but it gives you a feel for how many instructions the machine's going to be managing in flight. And from a retirement point of view, there's 8 instructions per cycle that this machine can retire. Now, as I said, the machine's built around kind of a balanced design. The decoders themselves can handle every instruction class in the processor, okay? Typical mapping from, I'll call it primary instructions that the ISA comprehends to micro-ops that the back end of the machine comprehends is very low. It's in the order of about a 2 to 5% penalty that you'll typically see in a machine like this. Moving on to rename, dispatch, and execution pipes. The register files are physical register files in the machine. Both vector and integer are around 400 total entries. This, as I said, feeds the downstream execution pipes, and there are a set of reservation stations that you'll find in front of these pipes. Kind of on the chart here, it shows you, and we'll see pictorially each one of these things later on, but to give you a feel, integer is 6 wide, the vector unit is 4 wide, and the load store unit is 4 wide as well. The integer pipe has a variety and a mixture of instructions and classes, which we'll see in the next slide. And the vector unit being 4 wide, each pipe is 128 bits. And it can handle basically every type of floating point format that we know today. So 32-bit mulls and adds, 64-bit mulls and adds, and it also supports 16-bit data types and a variety of formats, 8-bit data types for integer operations as well. But with that, let's jump to the pictorial side so you get a feel for what's in this machine. You can see the reservation stations at the top of the diagram. There is a general purpose register file that gets read after the instructions come from the reservation stations and start execution. Then they hit at the bottom of the diagram the varying execution units, as I said, 6. And the picture itself gives you a feel for the class of instructions that each pipe executes. You can see ALUs and shifters are present in all of the execution units. And then there's a variety of multipliers, dividers, branch execution units as well. And the notation that you see in the 2 black boxes on the lower right, that's basically what I call general purpose moves. They transfer data to and from the vector register file to the scalar register file that we have here. The vector data path is very similar to the instruction one. Basically, a variety of execution pipes and functional units that you'll see, multipliers, adders, compare instructions. Very similar layout to the scalar design engine. And you'll notice on the right-hand side, there is data movement coming in from the load store unit. And remember I mentioned there are 4 pipes. Those are the 4 data feeds to and from the load store unit. Now, load store, what is actually feeding this engine from the outside world? We have a large data cache in this engine. It's 96 kilobytes, runs at core speed. It has a 4-cycle load to use penalty that you see in a traditional design. It's multi-ported using a off-the-shelf standard bit cell that you'd find from the foundry, a classical 6T bit cell design. The translation, very similar to the integer side of the machine. It's a large 224 entry data structure. It's built to kind of balance timing and storage capacity for the physical or virtual to physical translation. We do support in the machine both 4K and 64K translation granules as well. Now, the execution pipe itself, what is load store actually built of? It's 4 fundamental engines. They can handle any combination of load store operations within the pipe. We support full forwarding. The number of in-flight load store operations you can see here to the outside world is quite high. 200 plus in-flight load store operations in this machine. And as well, there is a very tightly integrated L2 cache. Now, not diving into a lot of detail, but prefetching is one of the paramount things that you find in this architecture, in this machine. There are many, many advanced prefetcher algorithms, some proprietary, some that you'll find in industry standard papers. And if you catch me later on, I might give you a feel for what some of these are. But fundamentally, the algorithms that we have in this are simple line adjacency algorithms, next line prefetching or previous line prefetching, strides, pointers, arrays, pattern prefetchers. There's a multitude of them. And they're applied to both caches as well as translation structures. Okay. Pictorially, just like I had for the other parts of the machine, load store, you can see the diagram on the right-hand side. We have 4 reservation stations, and you'll notice that each reservation station has 64 entries. So there's quite a large number of in-flight load store operations. Each data path can handle 16 bytes per cycle into and out of the cache. That is done to match up with the bandwidth of the vector unit and the scalar unit. That interfaces to a 96 kilobyte cache and is all the incoming requests that are being managed. You can see here over 200 entries. And there is an interface to the integrated private L2 cache of 4-core complex, 64 bytes per cycle into and out of this underlying design. And then to the outside external world, it has a 32 byte per cycle interface. Now, the L2 cache, just a few tidbits here, a little different than what I call large capacity integrated caches. One of the things that you'll see in a lot of the designs that I've done, that cache has a tendency to operate at core frequency with very low latency. And the motivation behind this is the engine has to be balanced for data footprint as well as code footprint as well. And typically what you're going to see for large caches like this data footprint that's going to be sitting inside of this per core is somewhere between 3 and 4 megabytes of cache storage will be allocated to that processor. Now it can utilize all of it, but a typical footprint will be about that large. And that cache operates at full core speed with a latency that's averaging somewhere around 15 to 20 clocks, depending upon which part of the cache you're communicating with. Now the memory management, how do we actually structure the translation from virtual to physical? As I highlighted in earlier slides, there are a set of translation buffers at both the L1 level, but it's backed by a very large unified level 2 translation buffer. And this is done primarily to handle large data footprint. It's meant to handle all of the virtualized structures, the security layers that are there, but this structure is much larger than 8 kilo entries, which is very non-typical. And it's meant to try to keep the latency of translation down to an absolute minimum. This structure as well has prefetching mechanisms built in to try to bring in the translations well in advance of the load and store operations that it's consuming. As I said earlier, the backing structure supports the 4 and 64 kilobyte translation granules. It does support virtualization and two-stage translation, as well as nested virtualization in the design. And in terms of outstanding table walks in flight in the machine, it's not on the slide, but it's much larger than, it's somewhere between 10 and 20 in-flight operations per clock. Now, how at a high level does this set of CPU cores and processor clusters interface to the SoC? In a very simplistic way, the backing system has LPDDR5. It supports basically 135 gigabytes a second. The systems, which some of you may have seen out in the courtyard, there are some demo systems actually out there. Those systems support up to, and the SoC supports up to 64 gigabytes of DRAM. And kind of the last piece of information, and I know there have been many questions by the audience and on some of the forums, what type of cache is actually out in this SoC? And it turns out there's an integrated cache down below that the CPU complex and the SoC can utilize. That cache is 6 megabytes in capacity. And it can be used for all of the engines in the SoC. As well, with all of the interesting, I'll call it attacks that have been occurring in the industry against CPU complexes and SoCs, the CPU team has been spending a lot of time on security in order to try to help avoid any kind of breach of security within the CPU complex. And we've targeted via architecture as well as microarchitecture a bunch of different elements that have been integrated into the CPU in order to try to avoid these attacks. And you can see many of these styles that are listed here, some associated with side channels, authentication mechanisms. We have our own dedicated random number generator in the CPU. But the premise behind all of this was to avoid or try to minimize any kind of attack in the CPU complex and the SoC. Now, what do we see in a CPU that's built like this? What type of benchmarks and performance is expected out of a machine like this? So what I did here is I pulled together some data across various OSs and platforms, and you can see a variety here. There's Windows, there's virtualized version of Linux on Windows. You can see Linux as well, and kind of two standard benchmarks that the industry uses to measure these CPUs. One is Geekbench that you see here. The three tables on the left-hand side of this kind of give you a feel for the different OSs, scheduling properties associated with those OSs. But this is a single thread at peak operating clock. So this will be done at Snapdragon X Elites, top frequency of right now 4.3 gigahertz. And so you can see on this left-hand side kind of a range of scores. The variation is somewhere between 5 and I'll call it 12% based on where you look. But as well, I wanted to include for the audience internally measured data on platforms as well for both SpecInt and SpecFP for Spec 2017. So you can get a feel for how the processor is operating in classical integer benchmarks, kind of differences in OS stack where you see, again, Windows and Linux and how they compare and contrast, as well as floating point benchmarks that we measure in the industry. And the processor does hold up pretty well given some of the prefetch techniques that we've introduced. What does a latency of this CPU look like relative to the devices that are out in the industry? You can see on the left-hand side, there's a transition at 96K, which corresponds to the L1 cache capacity. This is a 4-cycle load to use. You'll see another transition occurring somewhere around the TLB capacity. That's where you see some of these transitions. And the large transition over here, again, is the L2 cache capacity at 12 megabytes. You can see standard stride-based prefetching schemes. The engine, the way it's designed, keeps the latency relatively uniform. And it looks like it's hitting in the L1 cache for the majority of the time. To the extreme where you see out here the latency is somewhere around, I'll call it 90 to 110 nanoseconds based on which aspect you're exploring in the CPU. The last one is the bandwidth. If you remember in the earlier slide, I talked about having 136 gigabytes per second of bandwidth available. This chart is showing you the bandwidth of a single thread given 2 types of load classes that the processor understands, vector loads, 128-bit vector loads. And the thing I wanted to highlight here is we see 0 to 100, roughly 130 gigabytes is here. The Lodestar engine is actually able to feed this single core with roughly just shy of 100 gigabytes a second, which means a lot to the CPU and its prefetchers. That's why you're seeing this offset be so high. Traditionally, I've seen machines operate in the 30 to 50 gigabyte per second, but we're able to actually push this near to 100. Lastly, where are we trying to take this CPU complex in the industry? You see it today showing up in compute with the CPU Orion technology, and there are a variety of segments within Qualcomm that we're driving towards. You can see kind of in the top, we have the compute platform that a lot of the demonstration devices outside are showing. There is mobile, there is auto, and then there is basically headset and VR. Expect to see a variety of devices appear in these spaces with this CPU complex and its future derivatives. And with that, we come to the end. So I'm going to open the floor up to questions now.
So let's start with a question from Slack.
Good morning, and thanks for your talk, Gerard. There's a couple questions around the cache, so let me combine these two. One of them was curious about why the data cache is smaller than the instruction cache.
It's primarily due to its timing. The load store loop, the 4-cycle loop of that cache is quite critical. Each cycle is running near its limits. We did study larger cache capacities as well, but it was driven by process more than anything.
Okay, and then also related to that, does the L2 concurrently support loads for the L1 iCache and Dcache?
It does.
Thank you.
George Kozma from Chips and Cheese. Quick question about the system level cache. Do you segment it so that the CPU can only, say, use 2 megs or 3 megs and then sort of dynamically allocate that, or could one part of the SoC use all 6 megs?
It actually, it can do all of what you described. Okay. It's a programmable engine as well, configurable element. There are biases built in for certain engines, yes. But any piece of IP in the system, if so configured, can actually access the whole cache, including the CPU if it wanted.
Okay. Thank you.
Jen Lee at FutureWay. Can I follow up with the SLC question in terms of the quantity, like 6 megabytes? given that L2 is already 12 megabytes for 4 cores, what's the decision making behind the 6 megabyte of SLC?
It's what you'll discover when you start measuring and looking at it. The SoC itself, predominantly minus CPU, is using that cache. The CPU can use it, but it's biased towards other elements, the video display engines or the GPU engine as well. But the CPU ends up steering away, as you rightly asked, because of its larger cache.
Okay, thank you.
Hello, I'm Makoto from Lenovo. You mentioned there are 3 CPU clusters, and one works like the efficient, the other works for the performance. Is there any hardware difference, or it was programmed by just a firmware software?
It's actually a physical construction difference only. From a software perspective, they look and feel exactly the same.
David Cantor, MLPerf. Congrats to you and the whole team on getting this delivered. Really exciting to see. Question for you on the L1 and L2. How many outstanding demand and prefetch requests do you support?
Just as many entries that are in those queues, actually. The prefetcher, there is a bias built in, obviously, but there's nothing to prohibit. If the load store engine is being fed efficiently, the prefetchers can actually utilize the whole structure if it wanted. There's nothing to stop it from doing that. Obviously, it's not going to do it on its own.
Right.
So there's going to be a natural balance that you'll find based on the instruction stream itself, inserting loads and stores into the queue and the prefetchers. And typically, you'll see that watermark. If the machine's running efficiently, sit around 35 to, I'll call it 50%, where it's normal load store and prefetch requests.
Got it. All right, thank you.
Sorry, I lost it in Slack here. So the question from Ravi at Intel is, do you expect to customize the core clusters into hybrid architectures, so different performance characteristics when you're customizing for the different segments?
That's TBD right now,
Okay.
but don't be shocked if something like that happens.
So it looks like other new architectures have kind of gone back and forth for reservation station granularity. And we've seen some people go more towards unified who'd been fine-grained. And you guys look like you went all in on, fine-grained granular per port stations. So how early in your design was that kind of foregone conclusion, or what led you guys to go with like the very highly parallel fine-grained design?
That concept actually was probably there from day one. The motivation behind it is I've gone and studied quite a lot of the other architectures, PowerPC, Intel, AMD's designs, all of them around the industry. What I tried to do fundamentally in architecting a lot of these machines, and the CPU's been trying to do as well, is to look at what I call every critical timing loop in the machine and remove them. Remove them as barriers. And the unified structure does have its benefits, by the way. It does have its benefits, but one of the elements of moving towards a machine architecture like this was to remove that scheduler's loop scanning ability and finding you'll hear people in CPU teams talk about finding the first instruction, finding second, third, fourth, fifth. And you have to do things in your machine to either break up statically the structure so that it's easy to find those things, or you go all the way to the style of design that I showed here, which is it's trivial to find. Because what you'll find in these structures, everything's a find first one.
Okay.
So it breaks the timing loop.
Thank you very much.
Chester Lamb from Chips and Cheese. You have a load store unit with a very large scheduling capacity, like 256 reservation station entries in total. That's actually more than a 248 total load store queue entries. So that's the opposite of how it usually is in other architectures, and I wanted to understand.
Why?
Yes.
Because you're trying to get the next set of operations into the machine. Basically, it's a balance. If you go smaller, you may find that there will be certain starvations. So in the performance model study that we did on this machine, It turns out, and timing-wise, it turned out that it was actually more beneficial to grow the capacity. And those structures, by the way, don't handle just load store operations. It does other things as well, so that those things will end up taking up capacity. So we're balancing all what I call traditional load store instructions and other activities that they operate on.
Thank you.
Oh, okay.
Okay, this one's from Daniel Dang. It looks like a lot of resources were allocated for conditional and indirect branch prediction in Orion. What was the reason for so many resources to be focused there? And then on top of that, a little bit of how did you make power performance trade-offs for adding these predictive structures?
Yeah, that's a good one. What I didn't show in the slide set here, when you're looking at a machine like this, it shows the potential peak capacity of 8 instructions per clock. The predictive structures, if you think about the nature of programs and you start studying x86 or ARM or RISC-V, any of these architectures, and you compile the code, there's a rule of thumb that kind of emerges that you'll find when you study code segments and fragments, that there's a branch 1 in every 5. Sometimes people call it 1 in every 4, sometimes 1 in every 6, but let's just call it 1 in every 5 instructions. Every fetch group that this machine brings in has at least 1 branch, at least 1. So if you think about feeding this machine continuously with an average IPC of, say, 2, 3, or 4, because of these branches, you would like it to be 8 if it could be. You throw as much resource as you physically can that is both timing capable and, as you rightly asked that question, power efficient at the same time. You throw as much resource as you can at the algorithms for conditional targets, conditional direction, in order to keep the back end of the machine fed. If you don't do that, it's kind of a waste of hardware. You'll build all this back end resource and won't utilize it. So it's again a balance. And the method for studying that is actually, we've designed a performance model that's pretty detailed. And we study capacity, associativity, banking of the structures, how that's all done. We study that in minutia in order to figure out the right trade-off and the right size for those data structures.
Right, and obviously it's a large code set that you have to look at.
Correct.
To figure out which algorithms are going to be the
Yeah,
best.
and that's another interesting point that you make there from a code set point of view. People have a tendency to bias towards benchmark ABC. You'll see them do that. What I've learned in my career is that every benchmark, it doesn't matter where it comes from, Spec 2000, Spec 2006, Spec 2017, Geekbench, what do you call it? All of the Java virtual machines, large programs, server, data center, large-scale machines. It turns out that the properties of these code segments, they're useful to study every single one of them because they give you clues about what we've learned in computer science. Things like data structures, linked lists, pointers, queues, all of these things. They give you all these clues. They're in these programs, and the programs themselves help you study the machine's architecture and how to balance it. So it's not just a bunch of transistors. It does come from computer science. So,
in other words, it hasn't changed in the last 20 years.
No, it's the same. We keep learning new mechanisms to help advance the processing.
Okay, great. Let's thank the speaker. Thank you.
Bye, guys.
All right, the next speaker is Arik Gihon, who's the lead CPU SoC architect at Intel. He joined Intel in 2004, contributing to the design and architecture of multiple generations of client CPU SoCs. He has experience in CPU development, technology, structural design, logic, architecture, and SoC integration. For the past decade, Arik led the power management and power delivery architecture of Intel client products. He currently leads the client SoC hardware architecture team responsible for the delivery of Intel's desktops and mobile SoC architecture.
Hello, everyone. Excited to be here today. I'm going to talk about Lunar Lake architecture. This is very exciting for me since Lunar Lake is an opportunity to work on a specific segment rather than working on a full family of segments from the thin and light to desktop. And this enabled us to remove a lot of the constraints of building a CPU and optimize it. So we have focused on 4 main things, specifically energy efficiency. I wanted to show that x86 doesn't have any issue of going down and meet efficiency targets of mobiles systems. Second is exceptional core performance, continuing give double-digit CAGRs of performance, bring graphics performance into mobile and gaming, and obviously AI capabilities into the PC. So Lunar Lake is built of 2 main tiles. One is called the compute tile, and the second is the platform controller tile. They are the top tiles, and they are built upon a base die. The compute tile is manufactured on TSMC N3B, and the PCD is on TSMC N6. Base dial is on Intel's 1227, and they are connected via Foveros technology. We also introduce memory on package, packaged together with the dice. The memory and package actually have 2 big advantages. One is power, enables us to optimize DeFi specifically for low power due to a low interconnect as well as a specific optimization for memory and package. And the second is footprint on the motherboard, which goes up to 250 millimeters square. It also helps meeting high frequencies, and as you see, Lunar Lake reach up to 8.5 gigatransfer per second. So we are focused in the SoC in 4 main architectural framework changes. One is compute die structure. We have redesigned the compute structure, in which we have built an optimized XPU type of die. The second is we have added for the first time a memory side cache, physical cache into the compute. The third is enhanced E-core cluster for efficiency, and which I will talk about, which is meant to contain most of the workloads that we run on the Lunar Lake CPU. And the fourth is a new power delivery scheme, a very fancy one, with power management scheme that supports it. So for the compute tile, as you see, we have the 4 P cores, Intel P cores, each of them with 3 megabytes of cache and of L2 cache and 12 megabytes of L3 cache. We have a cluster of E cores with a resized L2 cache of 4 megabytes. A media engine, the NPU engine, neural processing unit, graphics engine, and they are all built on top of a single fabric. Together with that, we have the memory subsystem on the same die for better latency and memory improvement, as I will show next. So the memory side cache, it's an 8 megabyte of physical cache. It is meant to reduce the DRAM bandwidth as well as reduce power by reducing the bandwidth and accesses to the DRAM itself. We have enhanced it both for latency and bandwidth, as I will show later. And we are able to cache actually every agent on the system. It's mainly for the CPU cores, as well as for the NPU and other I/O domains. The enhanced eco cluster, if you're familiar with the previous generation, that we have a low power island in Meteor Lake CPU, in which there we have 2 cores residing in the SoC die. Here we have 4 cores cluster, so we have doubled the core count. We have increased the L2 cache into 4 megabytes. We have actually located these E-cores on the leading node on the compute die. We are using the memory side cache to supply high bandwidth. So this adds additional IPC, as you will see. And we have independent power delivery for it, so it is a very optimized cluster. From power delivery perspective, we have designed dedicated 4 PMIC chips on the board. It's a single chip, duplicated 4 of them, and they are used to deliver a luxury in power delivery. So we are able to feed each of the engine separately as much as we wanted to. So the memory subsystem and the PHY and the E-core cluster, the P-core cluster, all of them are supplied by different rails. So we could optimize power delivery and also manage them separately, independently on different loads. We have upgraded the power management. So the 4 E-cores and 4 P-cores are working a bit differently. We have scaled up in performance the E-core cluster, so it will be able to contain most of the workload we are running today. And for that, we have changed the balancing scheme in which we can allocate budget to the E-cores when we want them to be performing, or to the P-cores when we have intensive loads. We are still using the Intel Thread Director in order to balance the load and to select which load to schedule on which of the clusters. We have enhanced our sleep states to cope with modern behavior, in which the sleep states are much faster and with much lower energy to get in and get out. And this is because most of the wakes that we are seeing today in modern CPUs are waking up the cores as we have multiple applications running concurrently versus previous generation in which mostly display was waking up the system. We have a machine learning based workload classification, in which it classified the workload, understand which workload should be running on the E-core, which workload should be running on the B-core, and also shift them around per need. It optimizes the system in terms of performance or power, depending on what is actually running on the system. It also able to classify what is exactly running on the platform, whether it's something that is bursty, something that is intensive for performance, some casual use, and so we can select the right threads on the right cores. So with regards to the performance scores are, I would say, a revolution on the previous scores that we had. They went through performance and energy optimization. The big thing we have done is actually removing the simultaneous multi-threading. This core is currently running only a single thread. This was a trade-off, and it enabled us to optimize for single-thread performance, get the right performance, but also get much better efficiency, remove complexities, handling hyper-threading. The second thing was a complete overhaul of the microarchitecture. We had to do that once in several years, and this time we did a step function in optimizing the performance scores, optimize their area, optimize their efficiency, sometimes even sacrifice the frequencies in order to give better efficiencies overall. And the last thing, we have moved to a modernized design structure, which enabled us to shift the P-cores quite quickly between different processes and also build different configuration for different segments to ease the constraints of building a full family of products from thin and light 10 watt-ish segments to up to 250 watt desktops. So power performance and area optimization. We have also did finer clock control, in which we can control lower bins. Previously it was 100 megahertz. Now we are shifting to 16.67 megahertz bins. Better control of voltage and optimizing power. We have AI-based power management and algorithms to control prefetches and several prediction algorithms inside the core, as well as shifting a lot of the power management that we had on the SoC to the P-core itself, like thermals and powers and some of the frequency control. It's a much wider machine in which we have also splitted the out-of-order engine into vector and integer as a whole. As you can see here, IPC, this is the S-curve with a gain mean of 14% improvement versus the previous generation Redwood curve. On fixed frequency, this is 14% performance. You can see on the right curve that we have optimized more for the low-end power, in which we are reaching up to almost 20% in performance and lower in the higher end. But this is a big CAGR for the performance curve versus the previous generation. Some of it was also due to the removal of hyperthreading, which allowed us to give better efficiency on the low power. So one big thing we are proud of is the efficiency clusters or efficiency cores. There we did a big change. We went all across to increase the workload coverage in order to fit a lot of the workloads that we are running today on the CPU, just on those cores, letting the P-core sleep or being used for only intensive loads. So most of the loads, most of loads will be running on the 4 E-cores. We have also checked on previous generation on the amount of threads that are actually running on the system, and it seems like 4 threads will be sufficient to a lot of the casual loads. We've doubled the vector and NI throughput for the same reasons, and also increased the scalability by adding more cores and increase the cache. Wider, as I said, and due to time I will skip that. Huge improvement both from the microarchitecture itself, but also from the different SoC components, improving latency, bandwidth, the system cache that were added, the L2 that was increased to 4 megabyte, a 38x increase in ASTI performance, as a 68 increase in the floating performance versus the Meteor-like low power E-core. As you can see, very important thing, we can deliver the same peak performance of the previous generation LP core with only a third of the power, and also reach a peak of 2x the performance. This actually helps us to contain more and more workload on those efficient cores and enable overall efficiency on casual loads. So how those cores working together, we have improved the latency significantly. This is a graph of latency load to use to the memory. The improvements are across the board. You can see the differences between the Meteor Lake E-cores and the Lunar Lake E-cores. This is just a pre-production check versus Meteor Lake production. But this shows the ballpark of the latency improvements. And you can also see on the bottom graph, you can see the increase on the L2 cache of the Atom, as well as later on the system cache improvement, and eventually the memory latency improvements. I've also added a graph that shows the memory bandwidth is increasing by almost 3x for the Atom core, for the efficient core, which enable us, again, to use more loads on it. And in addition, for enabling multi-thread scaling or collaborative workload on all the cores altogether, we have improved the cross cluster latency by quite a lot, 3x versus the previous generation. So from almost 180 to about 50-ish nanosecond. So in the right table, you can see the per cluster latencies as well as the cross cluster latency. Cross clusters means between P-cores and E-cores. So the two cores together, they cover the full range, while the E-cores are much better in the low power range. The P-core can supply peak performance on the high range, and they are used for intensive load or when thermal budget allows for burst applications. This is an example of Meteor Lake in which it has 2 LP cores, 4 E cores, and 4 P cores on the same compute clusters. Since the E cores are not strong enough, they could not contain this, in this example, Teams video conferencing. Lunar Lake looks much different. As you can see in these graphs, the entire workload is contained on the E cores. This allows much better power, much lower power for Lunar Lake versus the previous generation, and this is what we aim to do. So, going to graphics, yet a big leap in Lunar Lake. It's a premium device. We've put a big hardware in it. The graphics device is the XE2 architecture, second gen of XE architecture, which is actually an architecture that goes to the client CPU integrated one, as well as to the discrete graphics. Same architecture for the first time here. It has improved utilization, so more of the U's are being used, therefore much more efficient. It's improved the distribution of the different components and the fixed function inside the graphics to allow a better coverage of workloads. And it comes with way much more software compatibility right at the launch. So at the heart of the XE core, we have the vector engine. As you can see, it changed from a 2 SIMD8 structure to a 1 SIMD16 structure for better compatibility and optimization. Together with the vector engine, we have the XMX, the XE matrix extension engine, that supports multiple data types in 2, 4, 8, floating point 16, bfloat 16 for better compatibility, and this what gives the AI significant boost in AI capabilities for the graphics engines. Overall, 1.5x of gaming performance that we deliver in Lunar Lake at the same power of Meteor Lake previous generation. We have 8 second-gen XE cores, and together with that, X large ray tracing units to support the XE cores. Total 67 of peak tops that this engine can deliver, which is the biggest I've seen in clients' PCs. One more thing that is very important, if you look at the previous generation, we couldn't build a graphic engine that could scale from the low end to the high end. Lunar Lake does it. As you can see, it scales from the low power envelope to the high power envelope, covers 2 different graphics engine. Meteor Lake H was a bigger one, and the Meteor Lake U, with much better performance per watt or much better peak performance overall. As I said, up to 1.5x. It has a variety of this is an average, I would say. This is an example of stable diffusion that we showed in Taiwan, just briefly showing Lunar Lake ends after 6 seconds, while Meteor Lake takes a bit more. This is the text that was written in order to generate this stable diffusion. And as you can see, Meteor Lake ends at 13 seconds, while Lunar Lake ended in 6 seconds. This is twice fast versus previous generation. Media engine and display engine, 2 new things. So media added the VVC decode or H.266, which is the new codec. And we have added enhanced ADP 1.5 for better power efficiency, together with DisplayPort and HDMI 2.1, and supporting 3 display pipes. This is an example of the VVC power reduction. As you can see, this is an emulated software VVC versus hardware VVC. 30-ish watts on software versus Lunar Lake running at 2.5 watt. This is the efficiency that we were talking about. Very significant improvement. With regards to the NPU, the neural processing unit, it was introduced in the previous generation in Meteor Lake. So we did a quite big boost in performance by increasing the CPU, the NPU size, and increased its clock and efficiency, as well as optimized the software stack for modern AI usages. So the amount of engines was scaled from 2 to 6 neural compute engines. We've doubled the bandwidth. And together with the neural processing engine, we have also added 12 shape DSPs to support overall 48 TOPS. So AI in Lunar Lake overall reaches 120 TOPS overall. As you can see here also in the graph, a huge jump in NPU power efficiency from the PNP graph, 2x performance at ISO power, and almost 4x performance in peak performance. Connectivity, we're supporting Wi-Fi 7.0 as well as Bluetooth 5.3 with enhanced also wired connectivity of Thunderbolt, 3 Thunderbolt ports, and PCI Express, 4 PCIe Gen 5, and 4 PCIe Gen 4. With that, I will conclude. So we have actually reached all the vectors that we wanted to touch upon. More than 20% multi-thread performance, more than 20% single-thread performance. More important, it delivers the single-thread performance of the previous generation at half of the power, which is something we worked hard for that. More than twice the performance per watt in productivity. The AI throughput is 3x versus previous generation across the different engine. We deliver 50% uplift in gaming usages. And for battery life, we have reduced the SoC power by more than 40%. Thank you.
I will take the first question from Slack.
It's a nice presentation, Arik. You have got so many questions in the Slack channel. I'm just going to pick a couple. Hopefully you can follow up later. But this one got a lot of upvotes, so I'm going to go ahead and toss it out there first. This one's from Amit, Srivastava from Marvell Semiconductors. You said the magic words AI in your presentation, so they're asking for more details on what you mean by AI-based power management. How is it different than activity-based?
AI-based power management means that we are sampling counters at runtime, and we are putting them into different models of AI, like a neural network, linear regression, depends which algorithm that we use, and we use many of them. And these models are outputting the things that we want to decide on, for example, frequency. We implemented PIDs, different controllers, VII models, and so on.
Okay, so you basically coded up a model with the decision trees that you would have otherwise had to hard code into the silicon in the past. Thank you.
Is the base die a passive interposer, or are there any active power regulation or logic components on that?
It's a passive interposer.
Thank you. Great talk. Quick question on the hyperthreading for P cores. You mentioned it helps performance improvement during low power regions. I wonder, is it like workload dependent, and what's the core and the non-core frequency ratio during the power scaling? Just try to understand why.
Yes, so to question, yes, it is workload dependent, but it moves the entire S-curve down, so it improves the efficiency on top of the old S-curve. Obviously, some workloads gain more than the others. The complexity of supporting SMT, the constraints it put on frequency, and the amount of logic we have there that is not always utilized correctly, as well as sometimes even increased voltage, had cost in efficiency, and therefore removed it helped both in area as well as in efficiency.
Thank you.
Okay, this one is around, you mentioned it briefly, the memory side cache. Is it analogous to system level caches that are common on smartphone SoCs, or what's its primary purpose?
Yeah, it could. Its primary purpose is performance for the compute domain. The second purpose is using as buffer for different I/O devices in which they can share data between them.
I have a question related to that as well. Where is the last level coherence directory distributed, and are all the accelerators coherent clients of that, or are they in a partition space to not have to send probe traffic back and forth between, P-core slices, for example?
All the accelerators are coherent. I didn't talk about it, but we have did some hierarchical coherent structure in which we have coherency agents and a home agent. Right next to the system level cache at the same hierarchy, we have a home agent that controls multiple coherent agents, which enables all the accelerators together with the core to work fully coherent.
So like a core's cache miss to memory, is it going to be checking a directory local to like the P-core cluster and then another directory in that adjacent structure, or does it have a fast path to memory for a quick miss?
It's a fast path to memory, and we have Snoop filters duplicated in the home agents.
Thank you very much.
Depending on which cores.
We'll take this question here, but please remember speaker and affiliation.
So I have a question about, for the AI scenario, is there, any way like, a optimizing or collaboration between the AI PC side and the server side? Like
Between what?
between the AI PC, and the cloud side, the server side, like for some, AI user case, like things like that.
If there is collaboration between the AI PC and the cloud, at the moment I'm not familiar with.
So far it's decoupled, right?
Yes.
Okay, thank you.
Okay, this one comes from Eric Swan on Slack. How much should vulnerabilities based around speculative execution and prefetching, like Meltdown, Spectre, et cetera, how did they affect your microarchitectural design choices?
Huge part of it, and I didn't mention, is actually SMT. It's a huge vulnerability. Some of it it affected some of the selection of removing SMT as well.
Did you do any particular strategizing about what other vulnerabilities might be available, possible in the system, and think through how you protect against them in advance?
Yes, we did. It's not something that I can expose here, but we did quite a lot inside the microarchitecture to make sure that those doesn't appear again.
So it's part of the conversation these days as you plan your architectures. Okay, thank you.
George Kozma from Chips and Cheese. Real quick, where is the AI model for the power delivery being run? Is it run on like just where is it?
It runs on internal microcontrollers.
Okay.
Several of them.
So not on the NPU?
Not on the NPU.
Okay, thank you.
Let's thank the speaker.
Thank you.
All right, next up we have Chris Berry. Chris is a distinguished engineer as part of IBM's Infrastructure Hardware Development Organization. He has 25 years of experience designing next-generation IBM server processors, specializing in physical design, technology, and design automation. As the chief engineer for IBM Telum II, he's excited to share innovations in this processor with all of you.
Good morning, everybody. I was told to adjust the microphone, so make sure they're okay, not in my way. All right. Today I'm going to be introducing to you two new chips that will go into our next generation IBM mainframe. Telum II, our new processor, with its on-chip data processing unit for I/O acceleration, and our dedicated AI acceleration chip, Spire. First, we want to set the stage for what an IBM mainframe does, enterprise is, and why we focus on things in the ways that we do. In the time it takes me to do this presentation, IBM mainframes all over the world will process financial transactions worth many billions of dollars. In fact, 70% of all financial transactions will go through an IBM mainframe. It will handle tens of thousands of insurance claims, and it will safeguard the medical records of millions of people. IBM mainframes are the backbone of IT infrastructure and are critical where the data and transactions being processed require the highest levels of security, availability, and resilience. I do want to double click on that resilience and availability bit. IBM Z stands for zero downtime, achieving 8 nines of availability. That's equivalent to 1 hour of downtime every 11,400 years. And it is that level of reliability that mainframe clients require for their most essential workloads. Of course, performance and scalability are important dimensions for mainframes as well. And across all those dimensions, mainframes are designed for purpose to run mission-critical enterprise workloads and are optimized across the stack, from the chipside design to the software that runs on them. Here's a picture of a new processor chip, Telum II. It contains 8 cores running at a fixed 5.5 gigahertz frequency. There are 10 36 megabyte L2s. There's a 24 TOPS AI accelerator and a brand new data processing unit for I/O acceleration. I'll tell you a few details about all of them over the next few minutes, but I'm going to start off with the DPU. DPUs are being widely used in the industry for handling massive amounts of data very efficiently. And mainframes handle massive amounts of data. One fully configured IBM Z16 is able to process 25 billion encrypted transactions each and every day. That's more encrypted transactions per day than Google searches, Facebook posts, and tweets combined. And that kind of scale requires I/O capabilities way beyond what typical compute systems can deliver. It requires custom I/O protocols to minimize latency, support virtualization for thousands of operating system instances, and can handle tens of thousands of outstanding I/O requests at any point in time. So we decided to leverage DPU for implementing those custom I/O protocols. And given all the communication between the processor and the I/O subsystem, instead of just connecting the DPU behind the PCI bus, we decided to put the DPU directly on the processor chip. We coherently connected it into the processor SMP fabric and gave it its own L2 cache. By putting the DPU on the processor side of the PCI interface and enabling coherent communication of the DPU with the main processors running the main enterprise workloads, we minimize the communication latency and improve performance and power efficiency, realizing more than 70% power reduction for I/O management across the system. Here's the overall structure of the DPU. The main portion of the DPU contains 4 processing clusters. Each cluster consists of 8 programmable microcontroller cores, each core with its own private 64 kilobyte L1 cache. Those 4 clusters and their cores are interconnected by a local coherency fabric, maintaining cache coherency across all 32 of the cores. That local fabric is what connects the DPU into that private 36 megabyte L2. And that L2 is what ties the DPU coherently into the overall processor SMP fabric. In this first use of the DPU for accelerating I/O, we restructured the firmware so those custom I/O protocols can run on the DPU cores. By connecting coherently into the main processor fabric, we reduce latency between the DPU and the main processors. For example, for new I/O requests, parsing of I/O request address lists, or updates of I/O status and interrupts. The on-processor connection obviously being much faster than performing those operations across the PCI bus. On the right side of this diagram is the hardware that makes the DPU function as an I/O accelerator. This hardware contains a queue manager that keeps track of all outstanding I/O operations and informs the firmware on the DPU cores when the next phase of operation is necessary for each request. The queue manager also manages the state across the system and uses that information to help maintain fairness and encourage cache affinity. The I/O accelerator also contains bridge logic to the off-chip PCI interfaces that handle address translations and make sure the correct memory locations are accessed by each I/O operation. There's a dedicated data path for bulk data transfers to avoid polluting the cache with the data as it moves around the system. There's also additional hardware for CRC acceleration as part of that data bypass path. This I/O acceleration logic is connected through that local coherency fabric to the DPU cores, enabling the I/O firmware running on the DPU to orchestrate the end-to-end I/O operation. Back to the scale of the system this fits into, a fully configured IBM Z will have 32 Telum II processors connected together into one large SMP system. The system has up to 12 I/O expansion drawers, each of which have 16 PCIe slots, enabling up to 192 PCIe cards to be installed on a Z system. And many clients do build out massive I/O subsystems, consisting of many network, high-speed storage, and crypto HSM adapters. And the entire design point of the DPU has been tuned specifically to deal with the size and scale of those configurations. Now move to the rest of the Telum II processor. For the core specifically, we enhanced the microarchitecture in a variety of ways to improve IPC. To name a few, we added to our branch prediction structures, leveraging those changes to increase prefetching abilities. We bolstered our out-of-order execution efficiency by increasing the size of some of the renaming register files. There were changes to our data cache and TLB to improve store write-back and address translation performance. And yes, spending my career in physical design, I do have to mention a few improvements that came from the PD side of things. We went after a variety of library enhancements. We designed a richer set of low-power latches. We made improvements to both our base place and route algorithms, as well as to our hierarchical large block synthesis process, all of which allowed us to realize a 20% area and 15% power reduction in our core, while simultaneously improving the frequency. Now this brings me to our caches. These caches are one of the most differentiating parts of our design and are critical for our high transaction and large database workloads. As I said, there are 10 36 megabyte L2s on the chip, one for each core, one for the DPU, and the 10th L2 we left floating. I'll get back to that in a second. Leading into the reduced core size and exploiting a denser SRAM cell, we were able to grow the L2 cache without impacting latency. Latency for an L2 hit is still ridiculously fast, 3.6 nanoseconds. And going back to that floating L2, in Telum, we introduced this concept of horizontal cache persistence, where the L2 caches communicate their available utilization and allow the other L2s to take advantage of it. We leaned into that capability. That's why we can add that DPU, have it take up the majority of 2 core slots, create that floating L2, and yet still realize significant benefit from that larger pool of cache available to the virtual L3 and the virtual L4. The system leverages that extra cache and turns it into meaningful performance improvements. All in all, the virtual L3 and virtual L4 have each grown by 40% in Telum II to 360 megabytes and 2.8 gigabytes, maintaining pretty decent latencies. The Telum II processor is designed in Samsung leading-edge 5-nanometer technology. Utilizing the 5-nanometer technology benefits combined with those PD optimizations I mentioned before, we could push the core frequency up to 5.5 gigahertz. And that's not a boost frequency or something that only runs on a few cores at a time. That frequency is continuously sustained across all the cores in the system all the time, independent of data center temperature, workload behavior, really anything. It just runs at 5.5 gigahertz. In contrast, many other processors are modulating frequency to reduce power when idle or in a reduced workload state, or to limit TDP when intensive workloads are running. For mainframes, that's not really a viable strategy. Our clients require the performance to be consistent and predictable, in particular in high-load scenarios, and for that performance to be instantly available when switching from idle to busy. And historically, that requirement has added a bit of power overhead, needing to dial in the voltage to ensure support for high-intensity workloads or instantaneous workload arrival. Otherwise, dramatic changes in current draw could create error conditions, which for IBM Z is completely unacceptable. So we created a new voltage control loop capability in Telum II, significantly improving power efficiency while maintaining that constant 5.5 gigahertz frequency. It's tightly coupled to our power conversion subsystem, and by monitoring both the workload and the workload-sensitive areas throughout the design, we can constantly run at 5.5 gigahertz while adjusting our voltage based on the needs of the workload. This approach saves over 18% power across the processor for our average utilization workloads, and even more for any of the backup capacity our clients often have in the system. Another area that's really exciting is what we've done in the AI space. On Telum II, we've updated the on-chip AI accelerator, which we introduced with Telum 3 years ago. But we are also introducing the new dedicated AI acceleration chip Spire. Both the AI accelerator and Spire have been designed specifically for our clients' AI use cases. Many AI problems, like fraud detection, insurance claims analysis, or medical image analysis, fall within the realm of traditional predictive AI, using something like a CNN or LSTM model. Those AI models, while they don't get as much attention of late, provide very good accuracy, energy efficiency, and they do generate real business value. However, there's a lot of activity around large language models. And those traditional models don't always return a high confidence score. Sometimes you need a larger, more complex large language model to be deployed to provide a higher confidence answer. What we've seen is deployment of a relatively small, fast, energy efficient model as a first pass, and then only run the transactions with low confidence scores through a larger, less energy efficient model. We need to improve prediction accuracy. We call this model, this tag teaming of two models in concert with each other, ensemble AI. And it resonates well with our clients as they try to optimize their use cases. A good example of this is fraud detection. Tens of thousands of credit card transactions occur every second in many mainframes. And for some very high percentage of them, the smaller, more efficient model returns high confidence scores. But for a small percentage of them, you may need to engage that larger, more complicated model to get to an acceptable confidence level. And by tag teaming the models like that, using that small, efficient model most of the time, and a more accurate, less efficient model a lot less of the time, you strike a good balance across latency, efficiency, and accuracy. I'm going to spend some time describing how Telum II and Spire address these concepts, both the increasing adoption of traditional AI and the tag teaming of models to enable ensemble AI at scale. On Telum, we introduced that on-chip centralized AI accelerator. The benefit of that design point is that in a mixed workload, where the cores are spending most of their time doing database queries and transaction logic, when that workload happens to need AI, it gets the full power of the aggregated AI engines. One of the most unique features of the AI accelerator on Telum is its integration as a CISC instruction. Many processors implement accelerators through some form of memory mapped I/O, but that requires memory management across the hypervisor and OS stack, and often adds significant latency. To avoid that, matrix multiplications and similar AI primitives are directly implemented as CISC instructions. While the accelerator is doing the compute that the processor is offloaded to it, the main processor is performing virtual to physical address translation and access checking, and provides those physical addresses to the accelerator. This way, we minimize the latency of AI operations embedded in transactions. And I'll tell them the cores on each processor chip only had access to their local AI accelerator. And in the event where two cores on the same chip performed AI at the same time, they were time slicing access. As we are seeing increased adoption of traditional AI, that means the probability of such conflicts will go up. So we designed Telum II so that the cores can offload AI operations to any of the other 7 adjacent processor chips in the drawer. This provides each core access to a much larger pool of AI compute and reduces the contention for the AI accelerators. To improve overall model processing capacity of each AI accelerator, we are now supporting int8 as a data type, which is seeing increased usage as models are able to achieve sufficient accuracy even with that lower precision. We've also added new computational primitives as CISC instructions to better support large language models within the accelerator. Taken together, we've quadrupled the compute capacity of each accelerator to 24 TOPS per chip, and each core has access to 32 times more AI compute. Combined 192 TOPS per processor drawer, and there's now 3/4 of a petaops in a fully configured system. It's obviously a very significant enhancement to the on-processor AI capabilities. Like I said, traditional predictive AI still has tremendous growth opportunity. As I also said, we're seeing clients combine traditional AI with large language models to get even higher accuracy predictions. And given the sensitive nature of the data and the requirements for low latency, this demands additional AI compute directly in the mainframe environment. beyond what we can realistically support on the processor chip. And given the scale-out capabilities of our I/O infrastructure, the natural place to attach those additional AI capabilities is in the I/O expansion drawers. So we worked together with the IBM research team to productize a research prototype, enhancing it to fulfill the needs of enterprise environments, adding support for things like reliability and virtualization, as well as a mature model compiler software stack. And together, we designed a dedicated enterprise-grade AI acceleration chip, Spire. The chip sits on a 75-watt PCI adapter, surrounded by 128 gigabytes of LPDDR5 memory, which is plenty of memory to hold a wide variety of large language models in support of the heterogeneous workloads we typically see on the mainframe. With the I/O subsystem supporting up to 192 slots, this gives the necessary flexibility and capacity for each client to configure the right amount of large language model AI compute. Let's dive into the chip for a bit. There are 32 cores in Spire, which is the same shared base core design used in Telum and Telum II. Each of those cores has a 2 megabyte scratch pad for a total of 64 megabytes across the chip. We call it a scratch pad because it's not a cache. It's simply a place to put data for later usage. By co-designing the chip and the graph scheduler, which you would basically think of as a compiler, we can map the execution of the code to the topology and connectivity of the hardware, enabling us to manage the movement and storage of data since we don't need a traditional hardware-based cache management system. This has simplified our hardware implementation and enables us to continuously optimize the algorithms without an update to the hardware. And this hardware-software co-optimization has been so successful that we're seeing greater than 55% utilization of those cores during operation. Opening up those cores just a little, each consists of a pair of corelets, shown here. A correlet consists of an 8x8 systolic array of processing tiles, where each of those processing tiles is a 256-bit int8 vector unit. For accumulation and activation calculations, there are also 16 higher precision processing tiles within each correlet, for a total of 32 per core. There are multiple interconnection fabrics moving data around the chip. Neighboring cores can exchange partial results with each other on a high-speed 32-byte per direction bus, effectively creating a chip-wide bidirectional ring between the compute engines. A separate bidirectional ring with 128 bytes going in each direction interconnects the scratch pads. This allows for efficient movement of data from the interfaces to the cores, or to move data across multiple cores. There are 2 on and off ramps between the scratch pad ring and the 2 chip interfaces. And the LPDDR interface provides 200 gigabytes per second of memory bandwidth, which is well balanced with the total compute capacity of the chip, especially given the efficient data management the graph scheduler provides. Up to this point, I've been focusing mostly on predictive AI, which at the moment is where most business value is being generated. But with Spire, we will unlock even more compute-intensive use cases that the current on-die AI accelerator was never intended for, such as using generative AI for software developer productivity. Our clients develop huge applications, often with hundreds of millions of lines of code. With that kind of size and complexity, clients are looking for AI tools that can help them transform and modernize the codes more efficiently, help their developers understand the code better. And given that the code is a representation of the client's core business processes, specifically detailing how to run a bank or insurance company, it's very valuable. And they prefer, or maybe even require, that it stay on the mainframe. And for use cases like that, we have enabled Spire to support generative AI directly on the mainframe. Not for generic generative purposes, but to use it for specific use cases like watsonx Code Assistant for Z, to enable code modernization. However, a single Spire card won't have sufficient compute capacity for an interactive developer experience. For that, we're going to leverage that massive scale-out capability of the I/O subsystem, enabling multiple logical clusters of up to 8 cards. The firmware on those 8 cards will coordinate the distribution of compute and transfer of data amongst the cards, making those clusters appear to the software as one high-performance compute engine with 1 terabyte of memory and 1.6 terabytes per second of memory bandwidth. Clustering those Spire cards will enable our clients to perform the kind of compute-intensive generative AI that they are looking for, while being able to stay within the mainframe, giving them the enterprise-grade levels of availability, virtualization, and isolation that they expect from IBM Z. Of course, the Spire Accelerator is embedded in a sophisticated enterprise-ready software stack. There's card and host firmware managing the adapters, including error handling and recovery. The middle of the stack consists of OS drivers, graph optimizers, and performance libraries. The usual AI frameworks, PyTorch, TensorFlow, and Onyx support the accelerator. And the entire stack is then topped off by IBM's enterprise AI platforms, Red Hat OpenShift AI and WatsonX.ai, supporting IBM's purpose-built, customizable Granite large language models. All right, almost finished. Thank you for your time and attention. I'd like to thank the extended global IBM team that made these two chips a reality for the years of hard work, dedication, and innovation. There are a bunch of very proud IBMers watching this right now. I'm going to say thank you. Amazing job. Wait, one more thing. And finally, to highlight the significant jump in AI compute that will be available in the next IBM Z, we're currently building a test system that will have 96 Spire cards in it, which will have a total AI inference and compute of 30 petaops. That's the scale of additional AI compute we're talking about adding to our next generation IBM Z. And it will enable our clients to take their enterprise AI use cases to the next level. Thank you. Okay.
All right, for questions, remember to please state your name and affiliation before asking the question. We'll start with Slack.
So thank you, Chris, for the presentation, and you have a large number of questions in Slack that we're not going to get to, so please, if you can follow up, we'd appreciate it. This is sort of a joint question about the DPU. There was a lot of interest in it. So folks from Google and AMD and et cetera, we're all asking questions here. Is the DPU virtualized? How many virtual functions are supported, or does it run on some ISA? How exactly does the DPU get involved with the processors?
I don't know how to answer the question on whether it's virtualized. It's a internal ISA that we're not publishing. It's something that we're developing firmware for to run our workloads and our custom protocols and what have you. But I apologize, I don't know what virtualized means in this context.
Okay, sorry, I'm quoting the question. So.
Hi, Bing Yu from Andis Technology. I want to know the thinking trend behind using LPDDR rather than HBM.
For us, it was a design decision around sort of what we were going after in this form factor, right? We were looking for low power, right, and high capacity and I mentioned it in the talk, right? The mainframe runs a wide variety of workloads at any one point in time, and so we want to be able to have multiple models or lots of models in any given card at any one point in time so that any given workload can take advantage of it without having to reload memory and swap in and swap out. So that's sort of the main motivator. The second is it's a lower power form factor, which allows us to fit into our I/O infrastructure a little bit more easily and with a little bit more infrastructure changes. So for those two reasons, it was motivation.
Thank you.
Thank you, great talk. Jen Lee, FutureWay. I guess, allow me, I probably need some guidance here. So you have a on-die AI accelerator for traditional AI workload. You also have this new card for LLMs. Mm-hmm. And you have a notion of remote AI accelerator on die. Mm-hmm. And on die, you can also do LLM primitives. So how to put things together architectural level? So, and sorry, there's another related. So okay. For the on-die AI accelerator, you also have L1 cache. How big is that cache so that you can coordinate the workload, everything? There's an L1 cache for AI accelerator on-die, right?
Well, I mean, it has a small scratch pad with it, just like on it's the same basic, yeah, it's the same basic design as what's on that Spire chip. So yeah, there's a scratch pad there. But to go back to the previous question, right? I mean, yeah, it's a very sort of you can use it as you need to. Like you said, run large language models on the on-die accelerator. You can run them out on the Spire card. It's really about compute capacity needed for whatever you're trying to do, sort of the scale that's required, and then also latency, right? And the bank fraud detection, for example, that I use, right? you're talking about requirements on any given transaction of 1 millisecond response times and needing to be able to do that. So that on-die AI accelerator is sort of optimized for that sort of a workload. For that sort of enhanced fraud detection that I mentioned, where maybe 10% of the operations are going or need that larger model, right? You don't have the scale of compute capacity within the on-die accelerator. So that's where the Spire cards work. Now, that model works today on the on-die accelerator. You just can't run as many operations through that with that larger model as you will be able to Aspire. And so there's a variety of, the option space is broad, and in fact, as it has evolved with our clients and we see how they're adopting the on-chip AI accelerator, we're sort of predicting where we think they're going to head. And I'm not going to just try to highlight that I can foresee the future. I'm looking forward to seeing what they do and how they use it. But it's going to be about latency and model size and whatever else.
Got a real quick, how about the remote AI
accelerator?
accelerator?
And the remote AIU is sort of in the middle there. It's also for sort of load balancing across the AIs. It's a much lower latency than going out to the Spire cards, right? You saw the cache latencies are sort of reflective of what a remote AIU would be relative to the on-chip AIU or AI accelerator, right? You're talking sort of that order of magnitude of delta between having to go off chip to the other AI accelerator.
Ben Keller, NVIDIA, thank you for your talk. In the slide describing the AI correlate microarchitecture, it looks like you were doing some accumulation in FP16 and some in FP32. Can you provide any more details or clarity about that?
I don't know. What do you mean? What more details are you looking for in terms of what we're doing where or what transformations we're doing?
Is it simply a configuration where the user can set, please accumulate in FP16 or please accumulate in FP32? Or is it something more complicated than that?
So I don't know that it's user. I'm not an expert in the space, so I apologize. But I don't know if it's user specified as much as that firmware layer that I talked about, funneling the operations to the right compute. Okay. I can get back to you, though. I mean, there's people here that know that. Or
we can follow up offline.
Yeah, we can follow up offline. So catch me at the coffee hour.
Hi, Alan Cantle, Nalisway. Could you expand a little bit on the external memory architecture of the Telum II chip?
We've got each of the processors that has, we've got memory off of each processor in DCM, and it's sort of distributed across the drawer. So I didn't talk a lot about system topology because I was trying to pack in so much, but basically we've got 4 DCMs, 8 processors in a drawer, and we've got up to 16 terabytes hanging off of that in a system, or on 16 terabytes off of the drawer, and it is spread across the different DCMs, right? Because we have that very interconnected cache across the chips. The memory is also sort of distributed across, which in some cases isn't optimized for certain workloads, but for our overall sort of workloads that we're optimizing for, it works really well.
And do you still leverage the open memory interface on it, the protocol?
We do. Oh, I'm sorry, looking at my expert in the room. Yes, we do. Sorry about that.
Thanks.
Hi, Jeff Smith. Thank you for the great talk. So the 40% cache growth is a measurement primarily coming from allowing more of the L2 to be used as virtual L3 than in prior generations?
No, it's a physical amount of cache on the chip, right? We used to have 8 L2s at 32 megabyte. Now we're 10 at 36. And yes, the virtual L3 gets to take advantage of that, and the virtual L4 gets to take advantage of that across the drawer.
Okay. And one quick follow-up question, since that's the easy answer. This thing is a big chip. It's still sub-reticle. It's like 600-something millimeters.
Correct. Yes.
So when you guys were speccing this out for sizing, how did you decide to go with taking out a couple of processors and dropping in the DPU versus bolting on something more? And what is in that seemingly dead spot in the floor plan, if anything?
Oh, so the first part of your question is I really like that sort of question because it gets into sort of design planning and optimization, and it's all about how we balance what we're going after for that particular generation. And in this particular case, right, we could lean into better yields in 5 nanometer. Samsung's projections for 5 nanometer were looking like we could get more cores yielding than physical cores, on the previous generation. And so we leaned into that a little bit, and we didn't see the need to add more, especially with the frequency improvement and the socket performance and whatever else, to add more physical cores from a compute capacity perspective. And so we added a couple of rows there and put a DPU in the slot. From what's the space there? Unfortunately, it's just filler. It ended up being a little bit smaller than we had planned for, and since cores aren't exactly shrinkable and growable as the other stuff in the chip is, it just ends up being white space.
The DPU itself was not trivially scalable. It's not just
one question per person. Thank you. Sorry. Yes. All right, we've got time for one more question here.
Hi, this is a simple question. Dina Gankner from IEEE Spectrum. Maybe you said this and I missed it. What's the current status of the Spire chip? Is it available for sale now, or?
No, it's not available now. Both the system and the Spire chip will be available in 2025.
2025. Thank you.
Of course.
Okay, great. Let's thank the speaker.
Thank you. Thanks.